Ever find yourself adjusting a recipe on the fly? Maybe you're halving it or
You're
doubling it, or maybe you've tried to figure out how much paint you need for a room, and you don't want to end up with a ton left over.
Yeah.
Believe it or not, you're already using like the core ideas behind algebra.
That's right. It's all about patterns and relationships, and that's kind of what we're going to unpack today as we deep dive into a chapter from a mathematics textbook called 12 Algebraic Expressions.pdf.
I gotta admit, algebraic expressions doesn't exactly like scream everyday life, but I'm ready to be surprised.
What's really cool about algebra is that it gives us this way to represent these relationships with a sort of elegant shorthand,
Okay.
And the key to unlocking that shorthand is really understanding its fundamental building blocks, which are variables and constants.
Okay, so let's break those down. The textbook jumped right into those.
Yeah, it did. It used those classic X and Y examples. I think we all remember those from school. Maybe not so fondly. But think of variables less like these scary unknowns and more like, those adjustable settings on a washing machine.
Okay, I get that. The water temperature, for example, that could be a variable, right?
Exactly.
You can like tweak it depending on how delicate the clothes are or like, how stubborn the stains might be.
Precisely. And just like each setting on the washing machine determines, how the wash turns out, different values for a variable can actually change the outcome of an expression.
So variables are like the wild cards in the deck, right? Always keeping us on our toes.
Yeah.
What about those more predictable constants?
Yeah, constants are like the bedrock, the reliable elements that don't budge.
Yeah.
Think of them like the number of shirts you decide to wash.
Sure.
3 shirts, 5 shirts, 10 shirts, whatever that number is, it's constant.
So if we go back to my baking analogy, the amount of flour I need for a recipe, that's a constant.
Yes.
But the baking time, I might need to adjust that based on my oven or even the altitude I'm at, so that's my variable.
You've got it. You're thinking algebraically already. And see, that's the power of variables, right? They let us write these formulas that apply really broadly, not just to like one specific situation. So instead of having a recipe for only one size cake, variables give us a recipe for a on Y size cake.
That's actually a really cool way to look at it.
Yeah.
But how do we go from these like individual ingredients, the variables and constants, to actually putting them all together into an expression? The textbook used an example like 4x plus 5. What's going on there?
Okay, so imagine you're building something like a bookshelf, all right?
Okay.
You've got your pieces of wood, some long, some short. Those could be your variables because their lengths can change, right?
Right.
Then you've got screws, always the same size. Those are your constants.
Okay, so I'm picturing this giant pile of wood and a box of screws. How does 4x plus 5 tell me what to do with all of it?
That expression, that's like your instruction manual. It's telling you how to combine all those pieces. So the 4x might mean you need 4 pieces of a certain length, x, which you'll then connect to another piece. That plus sign is essentially saying, and then,
So if x represents a 1-foot-long piece of wood, I'd need 4 of those. Then that plus 5 must mean I need to add something else to the mix, maybe 5 screws to hold it all together.
You're getting it.
Yeah.
And just like that instruction manual guides you to build something tangible, an algebraic expression guides you to a mathematical result.
That makes way more sense than just memorizing that x is some like mysterious unknown.
Right.
It's more like x is a placeholder for a value that could change depending on the situation, just like the length of those pieces of wood.
Exactly. And the textbook kind of dives deeper into how we represent different types of relationships using what are called terms and factors. Think of it like this. Terms are the larger building blocks of the expression, kind of like the shelves of that bookshelf we were building.
So we're grouping parts of the expression into these like larger chunks, these terms. It's starting to feel like we're organizing our tool shed.
Right.
Put all the hammers together, all the screwdrivers together.
I like where your head's at. And within each of those groups, you've got your different types of hammers, different sizes of screwdrivers.
Right.
So those are the factors, the individual components within each term.
So going back to our trusty example, 4x plus 5, the text says 4x and 5 are the 2 terms.
Right.
And then within 4x, the 4 and the x would be the factors, right?
You've nailed it. The text even uses this cool visual. It's called a tree diagram to illustrate this.
Okay.
It's like you start with the whole expression at the top of the tree, and then you branch down to these bigger limbs, the terms, and then finally the individual leaves, the factors.
I'm a visual person, so I appreciate a good diagram, but the textbook, it also kind of threw in this curveball with something called coefficients.
Right.
I'll admit, that one always makes me a little nervous.
Don't worry. Coefficients are really just tag-alongs. They're those numerical factors that are, attached to a variable.
Attached how? Like with glue?
Well, more like with multiplication.
Yeah.
Remember we said factors are linked by multiplication? It's the same idea here. Like, for example, in the term 5y, the 5 is the coefficient.
Okay.
It's always stuck to that xy through thick and thin.
So it's like the XE is the celebrity and the 5 is their bodyguard, always making sure to, like, multiply them by the right amount.
Now, that's an analogy I won't forget. And here's why these coefficients are important. They help us spot the, what we call, like, terms. These are terms that have the same variable raised to the same power.
Okay.
And only, like, terms can be combined. Just like you can only add or subtract apples with apples, right?
Right.
Not apples with oranges.
That makes sense. You wouldn't want to mix those up in a fruit salad. So if we had, like, 3x plus 5y plus 7x, we'd want to combine the 3x and 7x because they're both attached to that x variable.
Exactly. And that's where our bodyguard coefficient comes in handy.
Yeah.
To combine, like, terms, we simply add or subtract their coefficients.
Okay.
In this case, 3x plus 7x gives us 10x.
So our simplified expression would be 10x plus 5y.
You're on a roll.
Yeah.
And just like there are different ways to organize, algebra gives us specific names for expressions based on how many terms they have. The textbook mentions monomials, binomials, and trinomials.
So those are based on the number of unlike terms, right? A monomial, like eighths, that's like a solo act, just one term standing alone.
Precisely. Then you've got your binomials like x plus 3, which are expressions with two unlike terms.
And if we want to like stick with our performance analogy, a binomial is like a duet.
Yes.
Two distinct parts, but they come together to create something new.
I love that.
Yeah.
And finally, we have the trinomials like 2x plus 5y1, which have three unlike terms. You could think of them as a trio, each playing their part in a larger composition.
This is making me realize that, like, even though we're talking about math, there's a real, like, elegance to how these expressions are structured, almost like a language itself.
It is.
But the textbook didn't stop there, did it? It went on to talk about actually, like, working with these expressions, adding and subtracting them.
It did, and this is where those, terms we talked about become super crucial.
Okay.
Remember, we can only combine terms that have the same variable raised to the same power.
So it's back to those apples and oranges. We can only add apples to apples, not apples to oranges.
Exactly. It's like combining ingredients in a recipe. You can't just throw in a handful of flour with a cup of milk and expect it to just magically turn into cake batter, right?
Right.
You have to follow the instructions, combining ingredients in specific ways to get the desired result.
So following the recipe carefully, we want to make sure we're only combining those terms, right?
Right.
But the textbook also mentioned like finding the value of an expression. So how does that fit in with all this?
So that's where we finally get to see our chameleon variables in action, changing colors right before our eyes.
Okay.
Remember, those variables represent values that can change, right?
Yeah.
So finding the value of an expression simply means like we're plugging in specific numbers for those variables.
So it's like when we adjust that water temperature setting on the washing machine, right?
Yes.
We're swapping in a specific value, like cold or hot, depending on what we're doing.
Precisely. And once we've substituted those values, then we follow the order of operations to kind of simplify the expression, and we arrive at a single numerical answer. The textbook gives the example of finding the value of 7 by 3 when x equals 5.
So we'd replace that x with a 5.
Okay.
So that gives us 7, 5, 3. Then following the order of operations, we multiply first, then subtract, and we end up with 32.
You've got it. And this is where those, abstract-looking expressions suddenly become really practical tools for solving, real-world problems. We can build formulas like for area, perimeter, or even something like calculating the cost of a road trip using these algebraic expressions.
That's right. The textbook mentioned that the area of a square is side length squared, or L. So if I'm trying to, figure out how much carpet I need for a square room, I can just use that formula, right?
Exactly. Just measure one side of the room, substitute that value for L in the formula, and boom, you've got the area of the room. No more guessing games at the hardware store.
I'm starting to see how useful this could be for home improvement projects.
Right.
No more, hoping for the best. It's
Right.
like, I can actually calculate it now.
And that's just, the tip of the iceberg.
Mm-hmm.
Algebraic expressions are the backbone of countless formulas and equations that are used in all sorts of fields, like engineering, finance, even music.
Wow, I never realized how much algebra was behind the scenes of our everyday lives. It's like a secret code we've now unlocked.
And like any code, the more you practice deciphering it, the easier it becomes.
Yeah.
You start to see the patterns, the logic, the sheer elegance of how it all works.
Yes. So we've journeyed deep, deep into the world of algebraic expressions, starting with those, like, basic building blocks of variables and constants, right?
We have.
We've learned how to identify terms, factors, and even those, tag-along coefficients.
Yes?
We've discovered how to combine these expressions through addition and subtraction, always remembering to keep those, like, terms together. And we've even seen how plugging in different values for variables can really unlock these, like, real-world applications of all these algebraic formulas.
Absolutely.
It's amazing how something that can seem so, like, abstract on paper can actually have such a, profound impact on how we understand and interact with the world around us.
It is really incredible.
And on that note, we'll wrap up our deep dive into this fascinating world of algebraic expressions. Until next time, keep those brains buzzing, and remember, even if you don't always see it, algebra, it's all around us.